Here's the plan for my topic. And first, we will talk about what Doris is. I will introduce its architecture and the main features. Then I will show how to build Lakehouse on Apache Doris. Finally, I will talk about the Apache Doris open source community. All right, let's dive in. First, what is the Apache Doris? It is the modern data warehouse for real-time analytics, offering super fast analysis on large-scale real-time data. Check out this diagram from the Apache Doris website showing where Doris fits in a big data platform. The upstream system includes the relational database data streams like Kafka and Pasa, and the data lakes and other structured and semi-structured data. And Doris can access the upstream data in two ways. One way is to import data into Doris using the pipelines and the processing system like Flink or Spark, or the Doris built-in import method, and then manage it as internal table data. And the other way is to query data directly through the connector framework. It can save time on data import and conversion, especially for data lake query acceleration. Finally, Doris can provide query service directly to end user for report and ad hoc analysis, the ELT data processing, and more. Okay, here's a quick look at Doris architecture. First, there are two main processes, the front end, or FE for short, and the back end, or B for short. The FE is handle the metadata, the cluster management, and the query planning. It is written in Java. And the B handle the data computing and the storage. It is written in C++. And from the version 3, Doris supports two architectures, the storage computation coupled and decoupled. The coupled architecture stores data on B's local disk. It is the classic MPP and share nothing architecture. It utilizes the local high-speed disk and the local networks to get a very good performance. But also the coupled architecture is not flexible because when scaling up, you have to add both compute and storage resource, which may not fit your requirement. And because both FE and B are stateful nodes, so you cannot to scale up or scale down in a very short time. And the decoupled architecture uses shared storage like the cloud object storage or the HDFS and a unified meta service. So you can see that FE and B nodes only need local disk for high-speed caching, making FE and B stateless for better elasticity. You can simply add a batch of nodes in seconds or shut down them at any time when you don't need them anymore. And also, you can easily create a multiple we call a computer group, and one for data read and another for the data write. So user can choose between these two architectures based on the simplicity, the performance, and the elasticity. Okay, now let's talk about Doris' main feature as an OLAP database. The first is lightning fast. It is one of the fastest SQL query engine. I will show some benchmark later. And I think this is the most important and the basic requirement of being a database or a data warehouse facing the OLAP or analysis scenario. The second is easy to use. Doris is very friendly for the first-time user. So if you know how to use MySQL, then you can use Doris too. It also has low operational cost as a distributed system. Most of annoying distributed failure are handled automatically by Doris itself. So, and furthermore, you can simply deploy Doris on various environments. The last is the material multi-scenario support. Besides the typical reporting and ad hoc analysis, it also supports a semi-structured data analysis and can act like as a Lakehouse engine, which I would like to introduce in detail later. So moving on to the query performance, I would like to use some benchmarks to show the performance. The first is the ClickBench, which is released by the Lakehouse company. It reflects the query performance on a single wide table with about 100 columns and 42 various aggregation queries. And you can see that Doris is the fastest query engine, only slower than the in-memory database like DB, and tuned version of Lakehouse. The other two benchmarks are TBCH and TBCDS. Because Lakehouse doesn't still prefer the multi-table join query, so we run this benchmark and compare to other popular databases. In the TBCH benchmark, we compare to a famous MPP database, Brainplum, which is a distributed version of PostgreSQL. You can see Doris outperforms the Brainplum by 5 to 10 times in average. And in TBCDS benchmark, we compare to other SQL query engine Trino, previously known as Presto SQL. And unlike the first two tests, in this test, both Doris and Trino are querying data stored in Hive table, which data is stored on remote object storage in Parquet format. And you can see Doris is 3 to 5 times faster than Trino in these cases. So you can see for both single table query like ClickBench and the complex, the multi-table join query like in TBC benchmark, and also for both internal storage format and the open source file format, Doris always provides a better performance than other alternatives. So Doris' excellent performance comes from many technologies, such as the code-based query optimizer, which provides hundreds of optimization rules, the C++ native vectorized query engine that can full utilize the modern CPU capabilities, and the columnar storage to provide efficient data fetching, the secondary index to search particular data quickly, and the materialized wheel to support the pre-aggregation data, and the smart caching for hot data analysis, etc. Since we are short on time, so I won't dive into the technical detail right now. What I really want to highlight is that Doris' impressive query performance comes from a tons of engineering work behind the scenes. Okay, the next is ease of use. Doris has a built-in MySQL protocol layer, so you can use any MySQL tools or libraries of any program language to connect to Doris. It also a relational database, so the database, the table, the column are all conceptions that you are familiar with. And most operations are done with standard SQL, like create database, create table, insert into, or select. So it's very friendly for the first-time user. Also, the deployment of Doris is very flexible. You can deploy Doris on everywhere, on the bare metal, the AWS EC2, the Kubernetes, and also my company, the ValueDB, also provide commercial products on cloud as the BLC or SaaS. So I think from the user aspect, Doris is very easy to get started. As a distributed system, we always facing node failure, the disk broken, the network error, but Doris can handle the cluster operation automatically, like repairing the data replica when disk is broken, or auto rebalancing node during scaling. It also supports adaptive concurrency control and the fault tolerance, so you don't need to worry about the high cost when managing a Doris cluster. Doris also supports the resource isolation, helping users to run different tasks smoothly within the same cluster. There are two types of resource isolation mechanism in Doris. One is a resource group, which allows users to separate the cluster node into different groups. And the different groups are completely isolated to each other, but the user can allocate the data replicas to each group so that to share the same data. The other is workload group. It is based on a C group. So user can limit the CPU, the I/O, the memory in fine-grained within a single node. So with the resource group and the workload group feature, you can easily manage the resource isolation both within and between nodes. Plus, the query fields feature help prevent unreasonable queries. For example, a user may execute a bad query, which costs too much CPU or I/O bandwidth. Doris can detect this situation and automatically cancel this query if the predefined thresholds are exceeded. It can also help to increase the cluster stabilities. And all in all, we are doing our best to make Doris easy to use, to help the user to get rid of all the system maintenance issues and focus on the data analysis. Okay, the last is the multi-scenario support. The purpose of Doris aims to solve multiple needs with one product, reducing the maintenance cost, especially for the company that do not have many people to operate too many systems. The first typical scenario is OLAP, the reporting and ad hoc analysis. The reporting scenario refers to reporting a task where query patterns are relatively consistent. So Doris can enhance query performance in these cases through techniques like pre-aggregation data model and various kind of data caching. Like I showed on this slide, there's a base table with 3 columns, the name, the department, and the salary. And we can create we call the roll-up table based on this base table with 1 dimension column, the department, and 1 matrix column, the summary of the salary. And Doris will automatically do the aggregation and materialize the aggregated data in the ROP table. So when users try to query this data, like select department, some salary from the employee table, group by the department, the Doris can automatically redirect this query to the ROP table and retrieve the data directly from the pre-aggregate data to avoid the computation at runtime. And the ad hoc query typically involve large volumes of data and diverse query patterns. So Doris can also leverage its MPP architecture and the adaptive pipeline execution engine to provide high throughput ad hoc query service. Doris supports various join operation, the inner join and the outer join, the semi-join, the anti-join, and also provide special join algorithm like the collocation join and the bucket shuffle join to reduce the amount of data shuffling during the execution. So that is why Doris can handle complex query in a very efficient way. The other two scenarios are high concurrency point query and semi-structured data analysis. A point query refers to the scenario where a small amount of data needs to be precisely retrieved from a massive data set with a very high number of concurrent requests, such as select star from a billing table where user ID equals 123. This is more like a get operation from a key value system. Doris optimized this scenario with feature like a hybrid row and column storage, which save the entire row in storage to reduce the column materialize time, and the short circuit query plan to avoid traverse all the optimization rules for this simple query. And the prepare statement can also help to catch the query plan for reuse. And thanks to this optimization, Doris can support tens of thousands QPS in specific scenario with very low latency. And you can see that Doris can achieve almost 30,000 QPS on a single node with very low 99 percentile latency. And the semi-structured data analysis is another area where Doris is good at, such as in log measurement. Doris supports inverted index, the full text index, and the flexible semi-structured data type like JSON and the variant. And many companies use Doris to handle terabytes of log data per day. So compared to Elasticsearch, Doris offers the significant advantage in terms of the write performance, the required performance, and the storage cost. Okay, I've briefly introduced the Doris feature in terms of the performance, the ease of use, and multi-scenario support. And now I will talk about one more important scenario that Doris is good at, to being a alternative Lakehouse solution for real-time analysis. So first, let's look at the three challenges that the Lakehouse solution faces. The first is how to enhance query performance on lake data. I think this is the most common and a nature need of a Lakehouse solution. Everyone wants to get results faster and faster. The second is how to measure diverse lake data, such as supporting the semi-structured data and the rapid data change, like the data insertion, deletion, and update. The third is the openness. Users don't like the vendor login, and the data should be able to be accessed by different compute engine for different workload. So let's look at how Doris can resolve these issues. Here, I divided the Doris-based Lakehouse solution into three scenarios: the query engine, the process engine, and the Lakehouse engine. First, like I showed before, as a query engine, Doris has a performance advantage over other products when querying data stored on Hive. So Doris also supports querying other popular lake formats like Iceberg, Hudi, and Paimon with the data stored as a Parquet or Orc. In our approach, we employ many advanced techniques to facilitate swifter analysis of lake data for users. For example, by utilizing the fire caching, we can cache the hot data on local high-speed disks, thus minimizing the network access overhead. And we also caching the metadata such as partitions, the file list in memory, so to facilitate the metadata fetching operation. Additionally, Doris provides a powerful materialized view feature, enabling the construction of a flexible materialized view from external data source with support for incremental refresh. Furthermore, the query optimizer support the transparent SQL rewriting based on the materialized view, allowing user to accelerate the specific queries without altering the SQL statement. The next scenario is the process system. And starting from the Doris version 2.1, a user can write data directly to Hive and Iceberg through Doris. For example, you can create a database via the Iceberg REST catalog and create a Iceberg table from Doris, and then write the data to this Iceberg table by using the insert into select SQL. And the Doris connector framework allows to connect to multiple data sources and do the federation query. So that, for example, you can simply query the data from a MySQL database and to do the transformation of the data and then insert the result into a Iceberg table. All are done in Doris. And Doris has a basic job scheduling framework, allowing for the orchestration of the scheduled job. For example, as I showed on the slide, a user can create a job to write the data from a Doris table to a Hive table every day at midnight. And additionally, Doris offers the spill to disk ability, helping user to executing the large-scale ETL task or the batch processing within the Doris using the limited resources. And moreover, through the materialized view, data can be processed in layers within Doris, like you can create the DWS and ADS data layer in Doris. The third scenario is using Doris as a Lakehouse engine. So we can observe that the currently popular data lake format, such as the Iceberg, the Hudi, the datalake, essentially offer a more manageable table format that supports data insertion, update, and deletion. But you can see that the Doris internal storage format can also serve as a lake formation. It supports the multi-version concurrency control, data insertion, deletion, and updates, and also support semi-structured data analysis. So you can easily import and manage data in Doris through various methods. And furthermore, Doris offers an open storage API based on the Aeroflight protocol. This API enables users to efficiently access data stored in Doris with the other compute engine, like the Python program, the Apache Spark, and Flink, and allowing data to flow seamlessly across multi-systems. These are the implementations of the Doris in the Lakehouse solutions. In future versions, we will further enhance Doris' ability to collaborate with a unified catalog system like a Unity catalog or Apache Graphitino project, helping users to better manage and analyze lake data within Doris. Okay, now there's a real user case, which is from Keva, a leading short video app provider, and they used to process data with Lakehouse and Hive and Hudi. Previously, they managed data on Hive and import data to Lakehouse to provide query service. So you can see they have to duplicate store the ADS layer data on both Hive and Lakehouse. And Lakehouse can only act as a query engine. And by replacing Lakehouse with the Doris, now they can query Hive and Hudi data directly without data import. It saves the overhead of data import and conversion. And also, they can use Doris' materialized view capability to accelerate queries, which is impossible with Lakehouse before. By upgrading the architecture, they build a Lakehouse engine instead of a simple query engine, and they not only simplify the data pipeline, but also improve the query performance. Okay, that's the end of the technical part of this presentation, and I hope this presentation will further helping you understanding Apache Doris. And finally, let's talk about the community very quickly. So the Apache Doris is one of the most active open source community in the big data area, and with more than 650 developers and more than 100 monthly active contributors. Compared to other popular open source community like Spark, Flink, and Iceberg, you can see Doris is vibrant and rapidly evolving open source project. And Doris is trusted by over 5,000 enterprises worldwide for online analytics. They use it in the industrial like the retail, finance, internet, gaming, and telecommunication, etc. So we warmly welcome everyone to join the Doris community. Here are some ways to connect us. And also the VeloDB is a commercial company based on the Apache Doris, and we offer cloud-hosted service for Doris, including both SaaS and BYOC, as well as technical support for Doris. So we invite you to connect us to further information, and you can connect us by email, LinkedIn, etc.